So in the last video on optimization, we started with a word problem. We defined our variables. We wrote our inequalities, translating the words into our inequalities. We rearranged the ones that needed to be rearranged. We graphed them all, we shaded, and then we found our polygon of constraints, where all of the shading overlaps, and we labeled our vertices A, B, C, D, E. I'm going to number our lines as well, just because it comes in handy when we're trying to solve for our vertices. So remember that the first line that we drew in was this line right here. So I'm going to put a 1 by this one. The second line was this one here. So it's going to get a 2. The third line we drew was this one here. And these correspond to our numbers here. Our fourth line started at 5. So this line here is our fourth line. Our fifth line was our x is greater than or equal to 0. So that's here. That's this one going up this way. And our sixth line was the one that was going this way. Our y is greater than or equal to 0. Now our job is to find the x and the y, so the ordered pair of each corner. So you can see that here, A, our x is 0, and our y, it looks like it's 20. Let's solve it algebraically just to make sure that that is, in fact, our ordered pair. So I'm just going to separate these off a little bit so we can do some work. A. Now, when we're solving for our vertices, we're changing all of our inequalities to equal signs. Now that we have our polygon of constraints, we don't care anymore about the greater than or the less than or the greater than or equal to or the less than or equal to. So we can rewrite these as if they had equal signs. So for point A, the two lines that go through point A are lines 2, which becomes y is equal to negative x plus 20. See how I changed this to an equal sign? And the second line is this one here, which is line 5, which is x equals 0. So I'm already told the x coordinate, and I can substitute that in here to find the y. So y equals negative x plus 20. I know that x is 0, so instead of x, I'll write 0. So y equals 0 plus 20, so y equals 20. So my ordered pair is 0, 20. Over here, I'm just going to start some notes. I'm going to write down our vertex. So we have A, B, C, D, and E. I'm going to write down our ordered pair, so our x and our y. Grading this table is a really handy way of just keeping track of what's going on. So A is 0, 20. And I'm going to leave one column over here that we haven't filled in yet, but we will. So A is done. Let's take a look at B. The two lines that go through B, line 3. So line 3 is x equals 6. And line 2 was y equals negative x plus 20. So I know my x is 6. I need to find my y, so I can replace x with 6. Y equals negative 6 plus 20, so y equals 14. So my ordered pair here is 6, 14. And I'll translate that down to my table that I've started. C, the two lines that go through point C are 3, which was our x equals 6, and 4, which is y equals x plus 5. Again, I know my x is 6, so I'll replace 6 here. So it becomes y equals 6 plus 5, or y equals 11. So my ordered pair is 6, 11. Let's do D, over here, I want to leave some space because we're going to do a couple more things with these vertices. So I'm going to do D down here so we have some space. The two lines that go through D, this is the most complicated point to find. It's 4, which is y equals x plus 5, and line 1, which is y equals negative x plus 10. Here we have to use our systems of equations, so we can use comparison or elimination or substitution to solve for x and y. In this case, I'm going to use comparison. See how I have these y's by themselves over here? That means that I can take this, my x plus 5, set it equal to this, my negative x plus 10, and solve for x. So I get x plus 5 equals negative x plus 10. If I add x to both sides, I get 2x plus 5 equals 10. If I subtract 5 from both sides, I get 2x equals 5. And then if I divide everything by 2, I get x equals 5 over 2, or 2.5. I have x equals 2.5. I want to know my y as well. So I can take either of these equations and substitute in my x. So I have y equals x plus 5. Y equals, well, now I know x is 2.5. So it's 2.5 plus 5. So y equals 7.5. So my ordered pair here is 2.5, 7.5. So I'll translate that over here. And then my last point, E, I'll solve over this way a little bit. The two lines that go through E are line 5. Line 5 is x equals 0. And line 1, which is y equals negative x plus 10. Well, I know x is 0, so I'll substitute in 0 instead of x. And I get y equals 0 plus 10, or y equals 10. So my ordered pair is 0, 10. Now, we aren't done yet. What we found are the combination of bears, x's, and dinosaurs, y's, that will give us the maximum value of the collection. But only one of these points is going to be the maximum. So what we have to do is we have to find our optimizing function. Our optimizing function is the one that has to do with the money. In this case, we want to know the maximum value. So our optimizing function is value. And how do we determine the value? Well, the bears are worth $10. So if we multiply $10 by the number of bears, which is x, so value equals 10 times x plus 15 times the number of dinosaurs, so 15 times y, we'll get the value of the collection. So this here is our optimizing function. We're going to use this at each vertex, at each point, to find the value that each combination of bears and dinosaurs would give us, and then we'll pick the maximum. So let's look at point A. Value, I'm going to rewrite that just as v equals 10x plus 15y. Well, we know x is 10, or sorry, x is 0 here. So value equals 10 times 0 plus 15 times 20. 10 times 0 is 0. And 15 times 20 is 300. So our value, that'll be our last column here, is $300. What this means is if he collects 0 bears and 20 dinosaurs, if this is the combination that he has in his collection, which is one possibility because it exists in our polygon of constraints, his collection would be worth $300. Let's look at the value for all of our other points as well. So value equals 10x plus 15y. In this case, X is 6, Y is 14. So the value equals 10 times 6 plus 15 times 14. 10 times 6 is 60. And 15 times 14 is 210. And so we get 270. So right now, if we just compare these two, A gives him a better value than B. That is, he'd rather have 0 bears and 20 dinosaurs than 6 bears and 14 dinosaurs if he's looking to maximize the value of his collection. Let's keep going. So V equals 10x plus 15y. V equals 10 times 6, because x is 6, plus 15 times 11, which is going to give us 60 plus 165, which is going to give us 225. So at vertex C, the value of his collection would be $225. We have 2 more points to look at. Vertex D, so here our value equals 10x plus 15y. So that is 10 times 2.5 plus 15 times 7.5. So 10 times 2.5 is 25. And 15 times 7.5 is 112.5. So 25 plus 112.5 is 137.5. And if we're talking about money, we'll add that extra 0. And then our last point, value equals 10x plus 15y. So the value equals 10 times 0 plus 15 times 10. 10 times 0 is 0. 15 times 10 is 150. So the collection would be worth $150 at vertex E. So what we see then is the maximum value of his collection happens at vertex A with 0 bears, 20 dinosaurs, and the maximum value is 300. So I'm just going to squeeze this in down here. Therefore, the maximum value is $300. And we are done with our optimization question. We've solved the maximum value of the collection.